Okay. So good morning. So thank you for giving the opportunity to be here and to present how mathematicians can cooperate with the engineers and in the industry. So as Anna said, I am Agnieszka Wyłomańska and I am representing the Faculty of Pure and Applied Mathematics. However, I am from the part of applied mathematics. Okay, so actually my presentation will be let's say starting point or some introduction to other presentations that will be given even during this session. Here I will explain how at our faculty we are cooperating with the engineers and how we solve the real engineering problems. So actually the vision of the cooperation is to use basic science with engineering applications, for engineering applications. And as usually, we have two perspectives. The first one, of course, this is mathematical perspective. So what we are doing, how it works. Actually, we try to observe engineers to identify the problem. Of course, at the beginning, it is very difficult to recognize what kind of problem they are discussing or they are solving. But the next point, which is crucial for this cooperation, is to define the problem in our language. So they are talking about some engineering, let's say, problems, and then we are trying to translate this problem into our language. And then there is, of course, the main point from our perspective, propose mathematical methods to solve the problems, and of course, one of the also crucial points, explain engineers the proposed solution, which is also, of course, not very easy, as probably you know. However, there is also the engineering perspective. Of course, they first are engineers, so they try to understand the object, design, technological process, of course, source of the signal, because here we are talking about the signal analysis, actually. So here we are talking about the vibration signal, so I will explain in a few minutes. And of course, then after the discussion with us, they try to use mathematical methods to solve this problem and at the end interpret of course, the results to give the solution to the, I don't know, to the company. And as you see, there is one common point. The common point is use mathematical methods to solve the problem. And actually, this is the point when we can cooperate with the engineers. Actually, we are cooperating with the engineers here from the mining engineering from many years. However, recently, we are working in two very important projects that are implemented at our faculty. So the first one is more research project financed by National Science Center. And this is the Shen project together with the Beijing University. However, in this project, there are also involved engineers. And of course, here is the name of the title of this project. But what is important, here we try to use mathematical methods to analyze the signals with non-Gaussian characteristics to identify the local damage. Here we are talking about the local damage detection based on the vibration signal. And we observe in the real industry that the signals have non-Gaussian behavior, non-Gaussian characteristics. And this is the first project that we are implementing now. And the second project that is also important for us, this is the project financed by National Center for Research and Development. And this is a project that we are doing together with the company AMC Tech from Krakow. And they are actually interested in the monitoring systems for mining machines, and they implement the mathematical methods, algorithms to identify the local damage. Okay, so here are the examples of the projects that we are implementing, and based on that, I will present what kind of methods we are using and proposing. Okay, so I want to highlight a few important points. So as I said, today we are talking about the local damage detection based on the vibration signal analysis. Why local damage detection? Because this is still a very hot topic, especially when the local damage is at the very early stage. So the feature corresponding to the local damage is not visible in the time series analysis and by using the classical methods. So this is the reason why we need still sophisticated algorithms, sophisticated methods. Of course, in the problem that we consider, there are few challenges. The first one is time-varying load and speed condition, meaning that the signal that we analyze is not stationary. As I said, the main point is the non-Gaussian background noise. Engineers are also interested in the identification of the multiple damages. So this is also very challenging for us. And the signal that we have, this is a mixture of many components that also do not help us to find the local damage. Here we are focused on the heavy-duty industry perspective. So as I said, we are working with the mining companies, KGHM, and they have a very big machines. You will see in 1 minute what kind of machines we are diagnosed. And this is really challenging problem. Of course, there is state of the art, and there are some methods that were used previously for this kind of problems. However, for the assumption of the Gaussian noise, classical approaches are related to the cyclostationary analysis. For Gaussian noise, we extend this methodology for the non-Gaussian noise. Of course, there are also the methods related to the optimal filter designs and source separation. And what kind of methods we are using? So robust measures, robust statistics in order to not take into account the large impulses observed in the signal, statistical modeling, and statistical methods. And I want to highlight once again that each method, each algorithm that we propose are related to the real object with the design and operation factors. And because we are mathematicians, we propose the algorithms that are based on the mathematical background. So we understand what we are doing. Okay, so here is the engineering perspective. Here you see the objects that we diagnose. My favorite is here. So this is a crushing machine that is working in the KGHM. I saw this machine in the mine. And this machine, according to the name, crushes the stones. Meaning, if the large stones, the big stones are going to the conveyor, first they need to be crushed. Meaning that the vibrations from this machine are, for sure, have very, very large impulses. And this is a normal, let's say, behavior. However, in order to diagnose if there is a local damage, we are looking for the cyclic impulses that are hidden in the noise. And this is a really challenging problem. And in a few minutes, you will see the signal from this machine. Okay, so on the left-hand side, you see still the objects, so the machines. And on the right-hand side, you see the signals. And this is exactly this translation from the engineering perspective to mathematical perspective, signal processing perspective. So here you see the exemplary signals, and you see very specific behavior. For instance, for the first one, we see the non-stationary signal. So the characteristics of the signal change along the time. This is visible here. Pure signal to noise ratio, meaning that actually you cannot see here the cyclic impulses because they are hidden in the noise. Of course, some maybe non-Gaussian behavior, and of course, time-varying characteristics of the signal. In the second signal, which is completely different than the first one, we also observe non-stationary behavior and also large impulses. And in the last signal, that maybe you can assume that it is stationary-based model. However, there is a very poor signal-to-noise ratio, meaning that the cyclic impulses that we want to find are hidden in the background noise completely. And this is also very challenging problem for us. Okay, so as I said, from the mathematical perspective, the problem seems to be very easy. Find cyclic impulses that are hidden in the noise. However, because of the challenges that I mentioned, this is not easy task. And actually, what is the state of the art in this area? So actually, there are two approaches. The first one is to find the impulsive behavior of the signal, because the cyclic impulses are also impulses, meaning they are, this is the impulsive behavior. And the second, let's say, approach is cyclic behavior identification. And in the first group, The classical approach related to the impulsiveness detection is based on the kurtosis. So Professor Jérôme Antony from INSA Lyon proposed a few years ago very, let's say, clever solution for this case. So he analyzed the signal in time frequency domain and applied kurtosis to the time frequency representation of the signal. Everything is easy. It seems to be easy. However, kurtosis, this is a statistic that is very sensitive for large observation. Therefore, kurtosis is not the best solution for the non-Gaussian signals, and we propose other statistic, more robust statistic that can indicate the impulsive behavior of the signal. In the second group, meaning the cyclic or periodic behavior identification, as I mentioned, there is a cyclostationary analysis. And in the classical version, the cyclostationary analysis was also devoted to the Gaussian cases. And here the classical measure of dependence, meaning the autocovariance, was applied. Everything was easy when the signal was Gaussian. However, if we have non-Gaussian signal with large observations, so the autocovariance or classical estimator of the autocovariance is not appropriate. Therefore, we propose other alternative robust measures of dependence related to this kind of signal. There is also the idea that combines impulsive and cyclic behavior identification, and this is the idea of the infogram. In our research, we also extend this idea for the non-Gaussian case. Okay, and now a few examples and a few solutions that we propose for the real industry. So, robust statistic, novel cyclostationary analysis, and measures of dependence for local damage detection based on the assumption of non-Gaussian signal. Okay, so in the case of robust statistic, we started actually 10 years ago to propose alternative statistics that are more robust than the classical kurtosis. And here you have some examples of the papers where we proposed for the real problems the new statistic. The idea is simple. Here you have my favorite object crusher. So here we assume that the signal, this is a mixture of many components: Gaussian noise, impulsive behavior or impulsive noise, cyclic impulses, and finally we obtain real signal. This is the real signal from this machine, 6 seconds. And you see there are large impulses, and you cannot recognize the cyclic impulses because they are hidden in the noise. The idea is to calculate the spectrogram for the signal. This is just a short-time Fourier transform of the signal, and for each frequency, we treat the spectrogram as a time series. So for each time series, we apply the measure of impulsiveness in the classical version of kurtosis to indicate the so-called informative frequency band. This is the band for which we have a different behavior than from the others. Okay, and this is the idea. So here we are looking for the frequency band for which we have the information, which is important for the engineers. However, as I said, kurtosis is very sensitive for large observation. Therefore, for the non-Gaussian cases, unfortunately, it fails. And in our previous research, we propose very known statistic that we know from the statistical lecture to indicate the impulsive behavior of the signal represented in time frequency domain. And actually, they are much more better than the classical kurtosis. And maybe this is a surprise for you. However, some of them, like JB test or JB statistic, is applied in a real monitoring system in the mining industry. Okay, so now in order to continue this idea of robust statistics, we also propose with Marcin Pitera and my previous PhD student, Justyna Hebla-Sopkowicz, the idea of conditional variance statistics. So Marcin and Damian also proposed the idea of conditional variance statistic and conditional variance idea for testing the Gaussian distribution. The idea is based on the 20-60-20 rule. When we analyze the data from the normal distribution and we divide the data into 3 groups in appropriate, let's say, division, we have the same variances. And actually, we continue this idea for the local damage detection, and we use the conditional variance statistic also as a let's say, replacement of the classical kurtosis as a new statistic, robust statistic that can indicate this impulsive behavior. And here maybe some results. Here we have a signals, simulated signals in order to control how the methods work for the special cases. And here we have four easy cases. So first, this is just a Gaussian noise without the cyclic impulses. So here we are not expecting the local damage. The second one, this is Gaussian noise with cyclic impulses hidden in the Gaussian noise. The next one, this is the non-Gaussian noise without cyclic impulses. So here we are not expecting the local damage. And this is the most challenging case. So the non-Gaussian noise, and inside you have the cyclic impulses that you cannot observe in the time representation. Here you have a spectrograms, and actually from the spectrograms, at least maybe here you can see some large impulses for the signal S3. This is the without local damage, and this is the most challenging case, and the informative frequency band is around 2 kilohertz. And for this kind, for signals, we applied our method. So the spectral kurtosis, another method that we proposed a few years ago, and the conditional variance-based statistic that is a robust statistic for the considered for this problem. And kurtosis completely failed for the non-Gaussian noise. Sorry, for the non-Gaussian noise. Here we are not expecting the local damage. However, kurtosis indicates something, which is of course bad result. And also here we have the bad result because kurtosis indicates the frequency band when we don't have the local damage. The local damage is somewhere here. So this is the very bad result because kurtosis is sensitive for large observations. Similar situation we have for our statistic called alpha selector. This is just an estimator over the alpha parameter from the alpha safety distribution. And once again, this alpha selector also indicates in this case something which is not good result. And here you have the result for the conditional variance-based statistic, and here the result is clear. In the case when we have a local damage, conditional variance statistic clearly indicates the informative frequency band that we assume. Okay, and here we have the real signal, the same from the crashing machine. So this is a spectrogram. Kurtosis completely fails. Alpha maybe indicates something, but the conditional variance statistic is of course very clear here, give us very clear information. This is the summary for the engineers. They also analyze the envelope spectrum here. Okay, and also with my former PhD student Piotrek Kruczek, we also proposed a novel approach for cyclostationary analysis when we are looking for the cyclic behavior of the data. So cyclostationary process in the classical sense means that this process has a periodic or cyclic autocovariance function, but not with respect to age, so lag, but with respect to time. So this is the idea. However, and in the classical version, as I mentioned, this methodology is based on the autocovariance function, analyzing time, and also in analyzing frequency domain. However, as I mentioned, the classical estimator is very sensitive for large observation. Therefore, Piotrek and our group, we propose a new approaches for this kind of analysis. So here we have a classical approach, by application, classical estimator of the autocovariance function. For the Gaussian case, we have a clear message, but for the non-Gaussian case, this method completely fails. And Piotrek proposed to apply the measure dedicated for non-Gaussian signals here for difference, which is more robust for the large observations, and we see that this codifference also works for Gaussian and non-Gaussian case, and this is in time frequency domain, and this is in time in frequency domain, and this idea is will be presented also by the next speaker, Wojtek Żuławiński, who is also doing the PhD to extend this methodology, and probably you will see more. Okay, and this is for the real signal. Once again, the proposition by Piotrek clearly indicates that here we have a local damage, while the classical approach proposed by big professors a few years ago unfortunately fails, because here we have some mess And this is also not good result here. Okay, and our last achievements are related to the second project that I mentioned. So the project that we are implementing with the company, AMC Tech company. And here we analyze the machine health prediction. And first, I will explain the problem, because from the mathematical point of view, once again, it seems to be very easy. However, it is not easy. So in the monitoring systems, from the people, engineers diagnose the machines, the vibration signals are collected. However, in the monitoring system, sometimes not the vibration signals are analyzed, but some health indexes calculated based on the vibration signal. Health indexes from the mathematical point of view, they are just a statistics calculated based on the vibration signal. And one of the classical approach is a RMS calculation. And this is the health index. And actually the health index, the exemplary, let's say, health index is presented here. And we assume here the model, which is called buff curve model. Why buff curve? Because when the machine is healthy, then the health index is flat. There is no trend. The noise is almost Gaussian. There is no changing the parameters. However, when the machine is going to the working state, the situation changes according to the health index behavior. Namely, the trend became, I don't know, maybe linear, maybe some more complicated function. The signal, so the distribution of the signal is not Gaussian anymore. This is maybe some heavier tails. And also the other parameters like scale also change in time. And this is the warning state, and we can assume that this is somewhere here. However, when we have the critical state, then the I don't know, characteristic of the signal completely change. So the trend, the scales are exponential, and the signal, the distribution of the signal is heavy non-Gaussian. And of course, many problems you can see here from the engineering perspective. How to find that the machine is going to the warning or critical state. How to predict the data in order to see when we obtain the so-called threshold, and how to calculate the rule. Rule means this is remaining useful lifetime. This is very important notion in the engineering perspective. Remaining useful lifetime from our perspective, mathematical perspective, this is first passage time, when the process exceeds the given threshold. So this is the information for the engineers. And actually, in this project, we are working on such problems, and we diagnose that there are many methods that people use in this context. Most of the methods are based on the statistical approach. However, we have also the new approaches based on the neural network, artificial intelligence, and also hybrid approaches. Okay, and what we are doing, so here is the signal from the buff curve model. And once again, this is the case when the machine is healthy. This is the case when the machine is the warning state. You see that in our model, the situation is different than in the first stage. And this is the critical stage when we have, of course, the worst case from the engineering perspective. And in our research, we diagnose the components of the models, and we build the models in order to simulate the scenarios for the engineers. And here is the real signal that we analyze. So you see in the real case, this is the object that we diagnose. The situation is much more complicated than we saw in the simulated signal. And this is just for the comparison that the real world is much more complicated than the simulated world and theoretical world. Okay, and what kind of, let's say, methods we propose here? Some of them will be also presented today. For instance, by David Szarek. So here we propose the framework how to analyze such kind of data from the stochastic processes perspective, and how to identify the components of the models in order to find the rule, to find the prediction of the data, which is important from the engineering perspective. We also work on the prediction of the data and parameters of the models. which is also important. And also we are working on the segmentation method, online segmentation method, in order to diagnose in which state we are. This is also crucial for this problem. And here you have some examples how we proceed with the data. So here we diagnose identified components of the model in order to recognize that this is really non-Gaussian case, that we have real problem here. And here we have some propositions how to predict the data, and more about this picture. I hope David will be talking in a few minutes. Okay, and now in order to summarize what we are doing. So mathematical methods have been used in various applications. Here you saw only one of the examples that we can work with the mining industry. And the inspiration for us is the Professor Hugo Steinhaus, who believed that there is no applied mathematics as a ready-made doctrine. It is created when mathematical idea comes into the contact with the semantic world. And this is actually this that we are continue. And here we prove that mathematics can be useful in the real problems, engineering problems, and that the interdisciplinary cooperation is possible, and such cooperation, of course, benefits both sides. Thank you very much.